Okay, hello everyone. Welcome to the day number 5, the fifth session and the last session of our QSilver workshop. So Przemek, if you are ready, the Zoom is yours and we can start.
Okay, thanks, Pavel. Good evening, everyone. So today we will be talking about the Shor's algorithm, which is basically the main topic of this course. And today you will use basically all or most of the skills and knowledge that you gained during this course. So Shor's algorithm is used for RSA encryption, yes? And let's start by formulating what this RSA cryptography is. So suppose you have two prime numbers, P and Q, and you multiply them. And as a result, you get a number called N. And uh, since those two numbers are prime numbers, we know that they are the only divisors of N. And N is our public information. So it is known, it can be treated as an input during decryption, but P and Q are secret. We do not know them. And to encrypt the whole message, we need to know P and Q. And this is basically RSA encryption, yes? So we need to multiply two prime numbers, and then we get a number N, and the public information is this number N, but the secret information needed to break the encryption are those two prime numbers. And the best known classical algorithm for solving this factored problem is because finding P and Q is also called factored problem. So the best known classical algorithm is the number field sieve. We will not dwell into how this works. But to factor an n-bit number, yes, so if n consists of a small n number of bits, yes, so this is n bits number, if we expressed it in binary, yeah, then the best known, as far as I know, yes, maybe something better was discovered in time, but the best classical algorithm, so this number field sieve, has a complexity of e to the power of n to the power of 1 divided by 3s. And if we use here big O notation, yes, it will look like let me move it here. Yes, we can use big O notation. Maybe it's a little bigger, yes. O. So it means that this is sub-exponential complexity. So it needs a lot of steps because we know that the exponential function grows pretty quickly, yes? So as the n grows, the complexity of the algorithm grows extremely fast. And even like the difference between sub-exponential and exponential for really big numbers is quite big. But if we get polynomial complexity that so a better algorithm, then the difference will be like not only big, it will be like huge, enormous. And today I want to talk about the Shor's algorithm, which has a polynomial complexity, which is much faster. Yes, so for while at the beginning, like it might be a little bigger, yes, But for big N, it will be much more effective than any non-classical algorithm. Okay, so let's start the procedure for our short algorithm. So to find P and Q, first of all, we need to pick a number. Let's call it A, and it must be between 1 and this big N, which is our known information. Yes, so pick A randomly. And as you should remember from the last lecture, this will be our input for the order finding algorithm. But before we apply the order finding algorithm, we need to do some checks on A. Well, because not every A will be a good number for us. So first of all, we need to calculate the greatest common divisor of A and N. So G, C, D of A and N. Yes. And if it's equal to 1, then we need to apply the order finding. Yes. Order finding algorithm. But if it's not equal to 1, then it means that we accidentally guessed P or Q. Yes? Then it means that A is equal to, for example, P, yes? Or A is equal to P, or to Q, sorry. A is equal to Q. But we need to be like extremely lucky to get this, yes? Because let's say today we will be trying this big number N to be like something between 10 and 100. So for number 10, we have about 20% chance of being lucky. For 100, we have 2%, which is still not that bad. But for real world applications, like we need to be like really, really, really lucky, and it's like more of being an impossible task to guess, like and the algorithm here, yes, where we have this greatest common divisor greater than 1. But usually we will have like this situation here. Okay. So then the second step, then we need to find the period, yes, that will satisfy this equation, yes. And this step is extremely hard for classical computers, but efficient for quantum computers using the period finding algorithm that we learned about. And then, okay, so I will maybe get here more numbers for that, yes. Here another like part. Once we guess R, that using this order finding algorithm and continued instructions, then we need to make sure that R is even. Or in other words, it can be divided by 2. If not, we need to restart everything. Yes, we need to restart the whole algorithm. If not, go to 1, 1. And maybe I think 2, 2, 1. Yes. And very often we will not be lucky. Yes, it's like more of a luck thing that we will guess the R that is even. But if it's odd, then we are just like need to restart everything, and we cannot do much about that. Yes, to protect us. So again, this is one of the part where Shor's algorithm is kind of random. And okay, so if we have an odd R, then we need to pick different A. Okay, and if it's even, then we can go further and calculate such number. So A to the power of R divided by 2, and then take the remainder of it. So if we divide by n, so we can notate it as follows. So we have a question how we choose R first. It is R randomly select. No, R, you calculate R from this equation, yes? So A is randomly selected by R. Okay, A is randomly selected, N is your input, it is known, yes? And R, you calculate R using order finding algorithm that we were talking about yesterday, yes? So basically this step here is all about using a quantum algorithm. So this is getting this R is the skill that we learned yesterday. And today I will show you like more code how to get this R, yes? But this like the theory behind it, like we talked about yesterday. Okay, so we get here R, we know that it is even. We calculated this expression. And then we need also another thing. So I will maybe mark it as the number, let's call it W. And then we also need to make sure that W is not equal to N minus 1. And why you, like we will talk about it a few steps later, yes, because if it's like it will be required for some to have some features that will be needed for factoring later. And if not, if it's equal to n minus 1, then we need to again start from the very first step. So pick another A. So it means that we again failed. So yes. And okay. And one interesting thing is that the chance that if we find R and it will meet both of these conditions, so that the R is even and this expression is not equal to n minus 1, so the probability is about like 50%, yes? So 1 in 2 twice will be successful, yes? So about half the time we will need to start everything again, because even if you find R, if you find correct R that is correct in terms of this equation, it might be not suitable for further steps that I will present you in a moment. Okay, here we have, yes. And those steps that I'm talking about are mostly classical, yes? So only this step is quantum. So we are talking mainly about pre-processing and post-processing after using the order finding algorithm, yes? Okay, and now once we have a good R, we can proceed to further steps of our post-processing. Okay, so we know that we find R that meets this condition. Yes. And if, and we can now subtract 1 from both sides, so we will get something like this, yes? And then if we can express this in also another way. Yes, because if we divide a to the power of r by n, then we will obtain some k times n plus 1 divided by n. Yes, so this is our remainder, in other words. Yes. So now I can make a shortcut and write here, yes, k times n, yes, because from this, yeah, because once we express the remainder operator in this way, we can extract k and plug it here. Yes, because we moved the remainder to the left. And then we can substitute n by using p and q. Yes, so we get on the right hand k times p times q, and on the left hand a to the power of r minus 1. Now we can use the shortened multiplication formula. So maybe I will use here x and y. X and y. Yes, x minus y, x plus y. Yes. And now we can express this in the following way. Yes. Minus 1 and a to the power of r divided by 2 plus 1 is equal to q. So this part also answers the question why r must be even. So there was, I believe, there's also a question on the chat about this. So this is like here you can see one of the reasons. And if you think about it, this part starts to look pretty like the problem that we are trying to solve, yes, because we have some multiplication here, yes. And now, since we know that r is even, we know that this expression is an integer, yes. So this whole expression is also an integer, and similarly, like this expression in this parenthesis is also an integer. So now, since p and q are prime numbers, we know that at least one of those two factors in those parentheses consists p or and q. So now let's write down what I mean by this. Yes, so we have three possibilities, and also I will express key as a multiplication of c times d. So the first possibility is that we have a to the power of r divided by 2 minus 1 times a to the power of r divided by 2 plus 1, which is equal to key times p times q, where this is c and this is d times p times q. Maybe to make it clear, I will write here cd, cd. Yes. The second possibility is that we have a to the power of r divided by 2 minus 1 again, and here the same thing, a to the power of r times divided by 2 plus 1. And now we will have here c times p, and here we will have d times q. Yes, and the last, third option is the a to the power of r divided by 2 minus 1 again. Here we also rewrite the expression plus 1 is equal to c d p q. And now we can see that this might be equal to c times p times q, and this will be equal to d. Yes, so we have three possibilities. The first one, where P and Q are encoded on the right hand side, so in the factor on the right side, and the left one contains only the part of K called C in this example. Here, both factors have one of those prime factors, yes, so, which will be important for us. And in the third example, in the third version, we have a situation which is like inverse to the first one, where only the first factor contains information about P and Q. Okay, so now let me show that the first and third cases are impossible. And I will do this by showing that for example, this case, those numbers are not multiples of n, because since we have k times n, we are looking for a multiple of n. Yes, because k times n is a multiple of n, because k is an integer. Okay, so let me start by writing this, yes, minus, maybe I will put a parenthesis here, yeah, 0, and write also mode, and here, and I want to show that this equation is not true, yes? Show it false. Okay. Okay, so if we add 1 to both sides, we get a to the power of r divided by 2 equal 1 mod n, yes. Then we know that r is the period of a to the power of some x or r, yes. Then it cannot be that r a to the power of r divided by 2 is equal to that expression, yes, because then it would violate this equation, yes, because r is the like smallest possible value that meets this equation. So if we found that r divided by 2 also meets this equation, then it means that our r was incorrect from the very beginning. Yes? So it violates the definition of order that we found. So if this equation holds true, then it violates, yes? Violates of R, because R is like the smallest possible, yeah? Oops. And okay, so we dismiss the first case, and now similarly, I will write here to 1 and here to number 3. So now let us show that a to the power of r divided by 2 plus 1 mod n equals 0. Mod n, yes, and show that this is false. Show it's false. So now if we subtract 1 from both sides, we will get something like this, yes? So we'll get here -1 mod n. Okay. No, sorry. Yes, subtract. So now recall that the modulus, so calculating the remainder, works in kind of a cyclical fashion, yes? So, for example, if we have this -1 remainder, if the remainder is equal to -1, then it actually means that we can also write it as n minus 1, yes? Mod n, yes? So for example, if we have like if we are dividing by 3, yes, if we are dividing by 3, then for the number 1 we get remainder equal to 1. For 2 we get remainder equal to 2. For 3 the remainder is equal to 0, yes. For 4 it's equal again to 1. Then for 5 it's equal to 2. And then again it's equal to 0, yes. So you can see a kind of a cycle here. And if we have this -1, then it actually means that we need, if we subtract from 0, 1, then actually it means that we will be ending here, yes? So if you have n equal to 3, then n minus 1 in this case will be equal to 2. So this is how we can interpret this -1, remainder equal to -1. We can change it to this number and nothing will be violated in terms of mathematics. And okay, and this is also not true because we also checked whether this number is equal to n minus 1. Yes. So this rule, like this constraint was needed to get rid out of this third case. Yes. So violates AR divided by 2. I will just copy it. Yes. Violates 3.4 maybe. Okay. And why we want to get rid of this case? Because as we will see in a minute, the second case, so this one, we are able pretty easy to factor it. Yes, so this will be the only case that will match the procedure of Shor's algorithm. Okay, so we are left only with the following case. Yes, so this is this. I will rewrite the second case. A to the power of r divided by 2. We have q p q, yes. And here we have c p and dq. Okay, that means that those numbers, yes, in parentheses, both of those numbers share a non-trivial factor with n. And by saying non-trivial, I mean greater than 1. Therefore, we can obtain this factor by calculating the greatest common divisor. Yes, so GCD, greatest common divisor of a to the power of r divided by 2 minus 1, and of course n. And q we can calculate also using GCD plus 1 and n. And that's it. We factored n. We breached the RSA encryption. That's basically the everything that we need to do if we are using the Shor's algorithm. So now let me give you an example. So example, and we will walk step by step to the Shor's algorithm. Yes. Example. Let's say that our input is n equal to 15. So of course you can factorize it in your head basically. Yes, using your brain. You don't need a computer for that. But now let's imagine that this is some very big number and you can do that math in your mind on your computer. Yes. So let's imagine that you have here a number that has like 8,000 numbers. So which is that big. Okay, so let's start. So first of all, we have this n and we need to pick a randomly. Let's say that we pick a equal to 2 randomly, yes? So we calculate the greatest common divisor for 2 and 15, yes? N. So you can clearly see that none of them share any other divisors than 1, yes? Because 2 is of course a prime number and it doesn't share any, like you can divide 15 by 2. So 2 and 15 are called coprimes, yes? They're prime with respect to each other, you know. So, yes? Okay, so we have this, so we calculated the GCT, and then we need to use the order finding algorithm, yes? So we need to find an R that will meet those this equation. So of course we will do it by using the order finding algorithm using a quantum computer. But now let me just move to Excel that I shown you yesterday. So I will open it and I need to switch the screen. Okay. So we have you don't see the screen, of course. Okay. Stop sharing. And now let me share this thing. Yes, so you should be able to see. Now you should be able to see the spreadsheet. Okay. So here we have this n equal to 15. Here we have a. Here we have candidates for r. So the exponents. Here I am raising a to the power of r. Yes. So a to the power of r, and the result is here. And here I calculate the remainder. Yes. And of course, R equal to 0 is a trivial solution. So then we need to go further, yes? So we have 2, it does not meet our expression. Then we have 4, does not meet. 8 does not meet. And here we have the remainder of 1, which meets our requirement. And here we can see that the R here is equal to 4. So this is our solution from the order finding algorithm. Of course, we will then we will use some programming to find R, but it is like a quick solution. So here we have R equal to 4. So I will switch back to OneNote. Okay, we are back. So we know that we calculated R to be equal to 4, yes? Also, we can see that 4 is even. Yes, so this is very good. And also, we should confirm that a to the power of r divided by 2 plus 1 is not equal to n minus 1 mod n. So here we get 2 to the power of 4 divided by 2 plus 1 and check if it's not equal to 15 minus 1 modulo 15. So here we have 5, yes, so we have 2 to the power of 2 plus 1, so we have 5, and here we have 14, remainder 15, yes. So we can clearly see that if we divide 5 by 15, the remainder is not equal to 14. And in most cases, this number here will be bigger than 15, yes? So I only warn you, yes? That for example, if we would have here 29, then like this equation would be true. And so we would need to discard R A equal 2 and start from the very beginning, yes? If like here we have this statement true, not false, yes? And okay, so we know that we have correct A and R. So now we can just calculate the factors. So we have E equal to GCD, so the greatest common divisor of A to the power of R divided by 2 minus 1 and N, which is equal to greatest common divisor of 2 to the power of 4 divided by 2 minus 1 and N, which is equal to greatest common divisor of 3 and 15, and this is equal to 3, yes? Because we can, the greatest common divisor of 3 and 15 is equal to 3. And I should also say to you that like there are many different algorithms for calculating the greatest common divisor. And you can use like any of your liking, yes? So it is like not very important in case of our course, but feel like we can do it in our head. Yes. So okay. So now we can also calculate Q, and we can, of course, do something like this, yes? It's not a problem. But it will also hold true if you do it the old way, yes? So using calculating the greatest common divisor of such an expression. Yes, which will be equal again. Here we have pi. Yes, we calculated it here, yes, because this is the same expression. And 50, which is of course equal to 5. Yes, we know the words are so 15 divided by 3. Okay, and that's it. So maybe let me give you an example where we'll get some result instantly. And so now let me just show you what will happen if we choose this A randomly, yes? So I will make here a side note. So if we have A equal to 6, so it does not need necessarily to be 3 or 5, and we calculate the greatest common divisor of 6 and 15, you can clearly see that this is equal to 3, which means that we find P or Q, however we call it, yes? And okay, so now we can simply calculate Q as and divide it by P. So it will be 5. Yes. Okay. So before we move to the Python notebook, I would also make a small remark that for now, quantum computers, as far as we know, are unable to break RSA cryptography because things like fault tolerance, because of noise and the size of this computer, so the number of available qubits compared to the size of the number n, yes, because the bigger the n, the more qubits we need. And of course, due to some security reasons, some encryption methods that are resistant to quantum computers are already developed and they are actually in use. Like if, for example, open, let's say, Google Chrome or other browser, you will probably see that there is a quantum encryption used for example, data storage. And such a cryptography is called post-quantum cryptography. Yeah? So it refers to classical cryptographic algorithms that are resistant to attacks from future quantum computers. Yes. For example, there is a class of encryption called, I believe, lattice encryption, and the encryption of such encoded information is hard both for classical and quantum computers, yes? But as for now, like I believe still the most popular, the most widely used encryption algorithm is the RSA algorithm, which is vulnerable because of the Shor's algorithm, yes? So that's why the Shor's algorithm is so important, because it is able to undermine the safety of encryption worldwide, yes? So that's also why we need post-quantum cryptography. Okay, so now let's move on to notebooks. I will also check if there are any questions, but I see none. Okay. Yes. Okay, so all the answers so far were answered. So let me open the notebook. I think I will also. Oh, I need to reshare my screen. Mm, this one, yes. Okay. Okay, so we are inside Shore's algorithm notebook. Here is, I will maybe proceed to task 4, like the other two, the other three. They gave you an approximation of this like 50% chance of picking correct R and A. So I will maybe, to make things a little bit faster, I will also just do this task for you. So here we are asked to factor 21. Okay, so first of all, we need to get some random A. Okay, so now let's, for that we will need some randomness. So we need to import random. And also NumPy will also be helpful because in NumPy there is a function for calculating the greatest common divisor. So we don't need to do this by hand as import NumPy as NP. So now I will be consistent with the thinking solutions. There is a counter. And now the first step, so picking a correct A that does not share a non-trivial divisor with n, yes, will be done inside this loop. Yeah, so let's say that now we pick this random number, so random range, and we want to select from 1 to n. Here is some counter, yes. So how many tries we needed. So this is just for our information, like it's not necessary, but nice to have. And now the function for calculating the greatest common divisor, we can use the one that we already have in the NumPy library. We check whether this is equal to 1. If it's equal to 1, then very good. We have a good start. Then we need to use the Shor's algorithm. If this is not met, then basically instead of picking another x, we should basically end the whole algorithm and just proceed to calculating the greatest common divisor, which will give us p. So we don't even need to launch the Shor's algorithm, yes, if this condition is not met. But here, since we want to use a Shor's algorithm, we just want to make this condition true. So this is just for us to be able to use the Shor's algorithm. So now let's print it. Print x. N is not okay. N. Yes, here n is equal to 21, and here we randomly picked 19. Here we can load the modular exponentiation operator, which is used in the order finding algorithm, as you should remember, yes. Then we need to create this this gate, yes, using the operator that we loaded. So UX is the general formula for this operator. And as you should remember from the previous lesson, we can create it by using such a piece of code, yes. So here we need to pass this random number and n, which is an input for the whole algorithm, yes. Okay, it should work. Here, we should load the QPE. So I believe it should work. if I do something like this, load QPE pi. Okay, we loaded this. Yes, so this is for the formula for quantum phase estimation. I believe we also need to load inverse quantum Fourier transform because we have IQFT here. So it will be, I believe, load QFT. Yes, okay, so we have it here, yes, so the formula for inverse quantum Fourier transform and here for quantum phase estimation, okay, and here we are told to load, yes, so I didn't notice that. Okay, now we need to determine the sizes of control and target registers. So for that, we will need a logarithm function, which we will import from the math library. So our n will be equal to cell of math log 2 of n. Yes. So the thing that we did yesterday. And t should be equal to 2 times n plus 1 plus a, and then we need to rewrite the formula below with some changes. So 2 plus 1 5. If it was here, 0.1 was the error rate, yes. So while n is like the number of qubits to express the n number in binary, t is the optimal accuracy of this of phase estimation. Yes, so we talked about the more numbers after the decimal point we have, the more accurate will be our estimation of the eigenvalue of our operator that we created here. Yes, but also like getting too many of them would be computationally expensive. Yes, so as you should have read in our notebooks, there is a pretty nice formula for choosing the right number of qubits needed for accuracy. Yes, and it's not defined out because yes, and now it should work. Okay, so now we need to start creating our circuit. For that, we will need circuit library, of course, and also Xscape, I believe. Yes, as far as I remember, yes. So we initialize our circuit. Yes, and then we create the control register. So we use the line qubit object. And as yesterday, we used list comprehension for that, with t plus 1. And I believe that yesterday, like I used here from 0 to t, but to be consistent with the notation in the notebook, like on those graphs, where they were like numbers from 1 to t, like so we will use this notation, yes, not from 0 to t, but from 1 to t plus 1. And our target register, yes, so you can see it, line qubit of I and range. Here I don't want to do the same mistake that I have done yesterday. So I set a proper beginning of this range plus n. Okay, and we also need to use XGate on the last qubit in our target register, yes? Target. And here the last one will be this one. Yes, because we have n qubits in the target register, yes? So the first one will have the index of 0 and the last one of n minus 1. And we want this egg because if you come back to the order finding algorithm lecture, we want to find a to the power of r equal to 1 remainder of n, yes? So this is because we have this one mode and this is for this one, yes? So using the XGate in the target register, we expressed the number 1 in binary. Okay, so now we can call the quantum phase estimation. So here we have P, control, and I believe we also have, yes, T, control, target, circuit, and our operator. I will just copy, paste it. Yes, and at the very end, we need to measure it. Yes, so circuit happened, circuit measure control, and key equal to result. Okay, that should work. Here we have already the simulator, yes, so we can print the result. Yes, and here we have this output vector. Yes, so here we have our input, yes, we change this qubit to 1, and here we have our output vector. So that's okay, yes, and let us now convert the binary output to an integer. No. Um, hmm. Let me see. Okay, measurement. Okay. Let me check what's wrong here. Let me check maybe N and T. Print N and print T. 5 and 14. 5, 3, 4, 5. So N is fine and T also should be fine. And let me sample it one more time. Oh, so I believe we were just extremely unlucky. Yes, so now it makes sense. Oh, yes. Because here, okay, okay. Um, yes, so this is um, our results from order finding algorithm. And now we need to use the continued fractions to find out the exact value of R. So here we have S divided by R. So here we can use the continued fraction function. So you don't need to write it by yourself. Cont frac. So this function cont frac is given to you. So here we want our number expressed in the decimal form. So this S divided by R, which is B. And here in terms of our the states that are inside the states, the amount of states that are possible to form using our eigenvalue register, yes? So now let's see what we will get. If it's correct, yes, it looks fine. So we can also use the convergence function that we have. And yeah, and print it. Okay. Um, see. Okay. Now it should work. It's okay. So we have here 0 and 1, 1 and 1, 2 and 3, and this pretty big number. Yes. So the candidates are, I would say, pretty big, I believe. So S equal to 2 and R equal to 3. Yes, it's like it's not correct, then you can also try this one. But our candidate will be this fraction. So S is equal to 2 and R is equal to 3 because those are like trivial. So R for sure like we already know that it won't work. And now we need to check whether R is even. So if R divided by 2, let me just print, okay, R divided by 2, the remainder, yes, the remainder is not equal to 0. So if we get an odd, then we need to print R again. Yes, it means that we failed. And as you can see, R is not even, then it means that we basically failed. And okay. And the second thing that we need to check, I will maybe already write a function for that, but as you can see, we will probably need to check other option. So I will just plug it here, plug it here. As you can see, this one is even, but now if so we need to check the second condition. So if x to the power of r divided by 2 and the remainder of this after dividing by n is not equal to -1, or maybe it's equal to -1, yes. So in other words, it's also equal to n minus 1. Then we need to start again. Yes. Oh, and as you can see, we have a problem here. with Python. We have a result to large. So I believe like under those circumstances, I just need to start again, yes? So let me start again. I was unlucky, and I find it kind of fun because it was not wrong for mathematical reasons. It was wrong because it was wrong because of my PC. So because of my computer. Yes. So now let's try. Oh, now we have x equal to 2. So pretty small, which is good. So now we need to try again. Yes. So we have here again n is equal to 5, but this time t is also equal to 14, yes, because it's independent from n. But here we will get a different result because our random number affects the CU operator, yes? So now let's simulate the results. Kind of don't understand why it does work this way. That's okay. Maybe if I run again. I'm not pretty sure why it doesn't work. Didn't work for the first time. Maybe I have a typo somewhere, which might be the case. Circuit. Circuit, circuit, circuit. Oh, I had a typo here. Okay, I didn't see it. Yes, or maybe not. Control target. Control circuit. Okay. Now let me call this again. The 14 qubits, so that's fine. Then we have another register, so that should be fine. Okay, so now we have another set of fractions. So we have, for example, 1 and t, and that looks good. So 2 is even, and it's not equal to n minus 1, or it does not give a remainder of n minus 1, yes? So it's not like equal to 20 after divided by 21, so that's fine. Yes, we needed here to repeat the algorithm, but not because of those two conditions, but because of the computational power of my computer and how big number it can store using Python. Yes. Okay. So now we can calculate P. So using the NumPy function, the latest common divisor. So x to the power of, and here I will need a function for converting to integer, yes, mostly for efficiency reasons, minus 1. Um, yes, so here is our x to the power of r divided by 2 minus 1. So let's check it. Oh, um, Hmm. So we have 4 minus 1, we have 3. What is n? 21. Check this number, maybe it's 1, 2, x. Okay, interesting. I never had a problem with that before. Yes, this is 2 minus 1. Okay. I check with 2 and okay, 3 is even, but if I check with this one, we got the R, okay. And okay, so I believe this is big. R. Okay. But if I compute plus 1, yes, then it's 3, so it's correct result. Okay, so I believe that should be okay. Maybe it was because of uh, I believe this is because of the accuracy of our quantum phase estimation. Yes, because it does not always yield the most accurate result. So it might be that our t was too small because like we had here this error rate, yes, and it was probably pretty too big. So here we kind of made a mistake that it's not purely mathematical, but it more depends on our own choice, yes. So here I kind of followed some kind of recommendation, and because of that, like I had too big error margin, and that's why I failed. Yes, so I believe like I have no luck with picking the correct number for the beginning. Um, so yeah, and okay, I believe like by showing why some results are not correct, like it was like a lesson that I did not expect to show to you. Yes, yeah, but that's also a result of how non-deterministic algorithms work and how the algorithms work if you do not if you set too big like error rate, yes, so not enough accuracy. Okay, because I believe we will be short on time, I will just move on to the next part of this lecture. So you have the solutions for uh, all of those tasks in, of course, the other to Python notebook. And I will also check whether something was incorrect here, but I think everything should be as in the notebook solutions. If something was not okay, if I discover something else, I will just note you on this. However, I believe that it should be okay. So probably it was just the case of choosing of having not enough accuracy for QPE. Okay, so now let's move on. Here I believe there are some pretty nice nodes in this Jupyter notebook. So the last one shows algorithm in more detail. So here we have our circuits for calculating QPE. Here we have our initial state, where we have those like zeros in the eigenvalue register and some eigenstate register, yes? And then as you can see, we apply here Hadamard gate, and then we apply those controlled U gates. So the one that you can simply upload. And then once we apply them, yes, we can see like we have this state, yes. So for K being the states of the first register, so the eigenvalue register, if we apply CU gates for some T qubit, so K with the small letter T. So if we have this key with small letter T equal to 0, then a new state will be kind of unchanged, yes? But for K equal to 1, we will apply this U gate like once, yes? So the thing that I believe showed you on Monday, yes? So we can write this in that way, here in this more elaborate way, where we have e to the power of something. And this, I believe I showed you during also on Monday, but with this expressed in the long form. And here we have this order finding, yes, so we have this formula here revisited. And here is the, as you should remember, yesterday I showed you a superposition of a to the power of r, of a to the power of k, remainder of n. But and we are talking about this equal superposition yesterday, yes, but here we have a instead of x. And there were also some coefficients I was talking about, and we were like changing the order of those coefficients, but here they are omitted, yes, as written here. We omit the multiplies here, so we focus only on the state inside of qubits. And here we have those powers ranging from 0 to r and then continued, yes? Which can be, in short, expressed in such form, yes? So here we have simply 1, because x to the power of 0 is simply 1. Here we have x, and so on, yes? And then again, since we have here r, which, as you know, should give you, if you find the correct r, should give you the remainder of 1. So this is equivalent to raising it to the power of 0 if we are talking about the modular exponentiation. Yes, so we can write this x to the power of r as simply 1, because this is like x to the power of 0 in terms of remainder. Yes, and you can write it and so on and so on. And now if we combine this register with the one we're talking about previously, yes, we will get a following state. So from the first registers, we have all the numbers from 0, then we have 1, 2, and so on. Finally r plus 1, r plus 2, and so on and so on. So we have like the integers here, one by one, yes, listed. And here we have like this register, yes. The second numbers are this register. So we have 1, then we have x squared, remainder of n, and then we start again, yes. So now, if you measure the second register and say you have some number j, yes, and the first register will be holding the integers k we are talking about a few months ago, such that if we write them to the power of k and calculate the remainder, we will get some number j that is observed, yes? So in other words, we can just express the first register in such a way, yes? So here you can see some kind of a pattern. And now, if you look again at this register, you can also tell what R is equal to, yes? Because you need to find at which point the qubit in the second register is again equal to 1. Yes? Because here you will find your R. Okay? And as you look here, you also get here some kind of a repeating pattern. Yeah? So you get here like R multiplied. Yeah, so this is like very nice formulation to read R from. Of course, like you cannot like directly read in what qubits, in what state your qubits are, but if you do it like mathematically, it that gives you a nice intuition. Okay. And here we have like the thing I also talked about when I was talking about the discrete Fourier transform. Yes, you will have here some kind of a periodic list, which will have the peaks around some n divided by r. Yes, so it will have the remainder equal to 1 if we divide n by r. Yes, so this, so we need to apply the Fourier transform to like invert this result. Yes, so to go from n divided by r to r divided by n, and to change the number of occurrences to frequency and the other way. Okay. So here we have like basically how to apply the QFT, but with other mathematical notation. Yes, here is this what we have seen. Okay. Here we also have, I believe, another example. Yes, here we have how to choose the size of a register. We have this error, yes, error rate. And here you have this like fancy formula I was like rewriting for a moment. Okay, and I believe the other information that are here I already told you yesterday. Okay. We have this implementation. Yes, here you can also look at R. This is also yes. So here you have 0, 1, 2, 3, 4. And by this 4 you have state get 1. So this yields you R. Okay, so here is this task revisited. Okay. Okay, so I believe that's all what I wanted to talk about today. So after today's lecture, there will be a quiz, and the quiz will be about, there will be some questions about the QPE, and like during the third quiz, you have some questions about how QPE works. Now you will have to need some intuition about the numbers. There will be, of course, the questions about the order finding algorithm, and finally some questions about the Shor's algorithm. And I like coding is not like required for this quiz, but I really advise you to browse through those notebooks because they will give you, I believe, some more intuition that I gave you yesterday. Yes, so on how some of those quantum states behave. Okay, so let me check if there are any questions in the chat. How to find if there's such a problem? Is there anybody able to track down? So I believe we are talking about the problem that I had.
Yes, exactly.
Okay, so first of all, if you have an R that meets both of those criteria, yes, those two criteria, and still you get an incorrect answer, then it basically means that you probably have some problems with these numbers, or you have some problems that are connected totally to randomness of the algorithm. Yes. So there is like no way to know that until you basically calculate the final result and something is not okay. But as you can see, we will, since measuring the state, it's like rather, I would say closer to the end of the whole algorithm, like you won't lose much, yes? So you will do continued fraction algorithm to calculate the convergence, check whether your R is suitable, whether it meets those two criteria, and then bam, you will get an incorrect answer, yes? So then you can simply either adjust the accuracy for quantum phase estimation, or maybe just start again, yes, from the very beginning. You can also sometimes try different combination of fractions from there. But as you can see in my case, like it didn't help because here I have R equal to 3, which is not even, and this number was too big to compute on my personal computer. But maybe it is correct. I don't know. Maybe it was like the case like this number 2, this convergent was not accurate enough, yes? Because the further to the right I go here, you can see there are bigger numbers, but this also means that the approximation of the true quantum phase is more accurate, yes? And as I chose only this 1 divided by 2, this estimation wasn't very accurate, yes? So I could switch to 2 divided by 3, which is more accurate estimation of like S divided by R. And here, like I chose this one, which is very accurate. But on the other hand, I was unable to use it because of the computational power of my personal computer, yes? So here I could, first of all, get more accuracy in QPE, so then I could hope that this estimation would be more accurate already, yes? But in our case, like it wasn't the case, yes? So probably this estimation is accurate enough. Yes, this one. But unluckily, I'm unable to compute it on my personal computer, yes, because here is this not very nice looking power. So that was the case. Or maybe if I put int there. Oh, okay, because I have number here, okay. Should it work? It does not work, okay. I will maybe this. Oh, so as you can see, this is a pretty big number, yes? So that might be the case why my personal computer has some problems. with adding the 1 and computing the remainder after dividing by, it was 21, I believe, in this example, yes? So it was like the problem with my personal computer, like it wasn't maybe the problem with the algorithm. Except, of course, if I used more accurate estimation, like I should get here some more accurate estimates earlier, not as big as here. Probably if I had even more qubits in the eigenvalue register, then I will get the maximum number of R will be even bigger, yes? So that's the case. Like you can adjust the precision of your computation for quantum phase estimation to get better convergence, and then you can basically try different convergence that you get here, that you receive here, yes, to deal with the problem. But in my case, like I either have the problem with the accuracy, so the number t, or with in other case, like the problem with the size of this number, yes, because if I raise it to such power, then it becomes just enormous, yes. Even if x is equal to 2, then raising 2 to the power of 8,000 something is like a very hard job for computer. Okay. So I believe that will be all. So please also browse through the notebooks. Remember that you have a deadline for quizzes and different tasks. I, of course, will be available on Discord like all the time. I will try to log in at least once a day, and I will try to answer your questions if you have any. And that's all, I believe.
Okay.
So, Paweł, if you like, just say a
Yes.
word.
Okay. Thanks.
And
Thanks, Przemek. Yes. Thank you. All right. Yes. Thanks, Przemek. Thanks everyone for coming today. That was the last session of our workshop, and as Przemek said, now we have several days to complete the assignments and quizzes in Canvas. Please remember to check the deadlines, okay? Because so take into account the time zones. Sometimes people are confused about the time zones, so it's always best to do the quizzes earlier. You have 3 attempts, as far as I remember, so do not wait until the end. Because we are not planning to extend the deadline, we feel that it's enough time, more than or at least 2 weeks for every quiz and every assignment. So it seems to be enough. And based on the results of the quizzes, we'll later generate the certificate. So it also takes a few weeks. We'll also ask you for a feedback. We'll share a feedback form later. And I think that's all. So as Przemek said, if you have any questions later, feel free to post your questions on Discord. So Przemek, our mentors, will try to answer. And we hope that you enjoyed this workshop and that you also attend our future events. We are planning to organize another workshop in April, so it will be focused on quantum machine learning. And then at the end of May or beginning of June, there will be a workshop on oracular quantum algorithms, QNiCal. There will be also some other events. So on Thursday, we'll have the next online episode of the Warsaw Quantum Computing Group meetup. Later this year, there will be a quantum hackathon organized by QPoland. So just follow our social media profile, subscribe to our newsletter, our YouTube channel to stay up to date. Thanks everyone once again. Have a good evening, have a good weekend, and good luck with the quizzes and the assignments. I'll now stop recording.